Polarity of molecules. Okay, so this brings back a concept that we've already kind of talked about, and that was electronegativity. So we talked about electronegativity, and the concept there and the key of electronegativity is that within a bond, if there is one atom that wants those electrons that are shared in a covalent bond more so than the other, that atom is considered electronegative. If you remember, with respect to electronegativity, we had some sort of extremes. The most electronegative element was fluorine, with an electronegativity value of 4. And that is compared to something like cesium. Cesium has an electronegativity value of like 0.7 or something like that. So within a covalent bond, the more electronegative element wants those electrons more, within that shared bond. And what that means is that's going to make a bond polar or nonpolar. What we can do with this information is determine whether or not a molecule is polar. Okay, so for a molecule to be polar, what we have to have polar bonds. Okay, an example of a polar bond would be this carbon-oxygen bond. Carbon is a little bit less electronegative than oxygen, in which case it has this sort of partial positive charge. And we already talked about how you signify that. This, effectively a positive here, is contrasted with this arrow, which effectively means a negative charge there. Okay, so we're showing where the more positive region of this bond actually is. Okay, now in order to understand whether or not a molecule, or deduce whether or not a molecule is polar, you have to know something about the geometry of that molecule. So you must have a geometry where the dipoles, so these two poles, do not cancel. Okay, symmetrical shapes tend to cancel out dipoles, and we'll see some examples of that in just a moment. So an example of a nonpolar molecule would be something like CO2. We've got an electronegativity between carbon and oxygen of approximately 1.0. So we took the 3.5, subtracted 2.5, we landed at 1.0. Okay, so that is considered. So this carbon-oxygen bond, sorry, my circle's not very good there. That carbon-oxygen bond is polar. This carbon-oxygen bond, likewise, is polar. We've got a partial positive area where that carbon is and partial negatives where those oxygens are. Okay, this is a nonpolar molecule despite having two polar bonds, because of the fact that these two polar bonds basically cancel one another out. I always kind of think about it like a game of tug of war. Okay, so you've got these two forces, these two opposite forces that, yeah, they're pulling, but they're pulling with equal strength. Okay, now if we compare that with a polar molecule, such as H2O. Okay, so let's think about the geometry of H2O. H. Then we've got these two lone pairs of electrons. Okay, so what do we know about those lone pairs of electrons? They're going to push those hydrogens down. So is water a linear molecule? No, it's not. It's considered a bent molecule because these two lone pairs of electrons occupy a ton of space, and they're going to be basically forcing those hydrogens away. Okay, so now what that is going to mean is your partial positive charges around these hydrogens, and due to the fact that they are not opposite one another, they're not going to cancel one another out because these lone pairs of electrons are occupying lots of space, preventing those two oxygen-hydrogen bonds from being opposite one another. So now some examples. If we take something like H2, well, H2, that's the sharing of electrons between two hydrogen atoms. Well, what's the electronegativity difference between those two hydrogen atoms? They're both hydrogen, so the electronegativity difference is 0. Okay, that's a nonpolar bond. Since it's a nonpolar bond, this is a nonpolar molecule. Okay, now carbon dioxide. We already looked at that as an example. Those are polar bonds. Each of those are polar bonds, but this molecule is linear, and therefore those dipoles, those two poles which are being kind of pulled away from one another, those are going to cancel one another out. Okay, so it is not a polar molecule. Now here we've got SO2. Well, SO2, if you look at this molecule, we've got a single bonded sulfur-oxygen bond and a sulfur-oxygen double bond. Okay, so when we think about those two individual bonds, well, we've got a polar bond there. They are both polar bonds. But if you look at that central sulfur, we've got a lone pair of electrons. So if we have a lone pair of electrons and a single bond and a double bond at oxygen, we do not have a linear molecule, we have a bent molecule. And since that molecule is bent, those two sulfur-oxygen bonds cannot cancel one another out. Therefore, this is a polar molecule. So these polar bonds don't cancel, therefore it's a polar molecule. Okay, some more examples. We've got BF3. Okay, BF3, if you look at that, where's our central atom? Do we have a lone pair of electrons on it? No, we don't. We don't have a lone pair of electrons. So what we have is 3 individual BF bonds. Okay, so those individual BF bonds, well, they're all the same. This is a instance where these 3 different atoms, they are going to be completely linear. So even though those are polar bonds, that molecule is a trigonal planar molecule. It's a linear molecule, or a planar molecule. These dipoles are equal to one another and cancel due to the geometry. Therefore, this is a non-polar molecule. NH3, nitrogen, hydrogen, that's a polar bond. Okay, but that central nitrogen has a lone pair of electrons. Hence, this molecule is trigonal pyramidal. That lone pair of electrons is going to prevent those nitrogen-hydrogen bonds from canceling one another out. So this is a polar molecule. CH4, carbon-hydrogen bonds. We've got 4 of them. Those are all polar bonds. That molecule is tetrahedral. These dipoles are equal and cancel one another out due to their geometry. So it's important to be able to understand what that molecule looks like so that you can kind of say, based on what the molecule looks like, based on the lone pair of electrons or all the different electron domains, I know that these will cancel out or not. Okay, so CH4 is not a polar molecule. Valence bond theory is one in which we use covalent bonds or kind of define we define covalent bonds based on the overlap of the valence electron orbital of one atom with valence electron orbital of another atom. Okay, the overlap allows 2 electrons of opposite spin to share the space between their nuclei. Okay, since both of these shared electrons are attracted to both nuclei, they act like effectively a glue and they form a covalent bond. We're going to go into this a little bit more in the next video. We're going to be getting into what are known as sigma and pi bonds, but that's kind of this valence bond theory is you have overlapping electron orbitals, and that is how we're able to get these electrons to share with one another. Now, what I hope you took away from this video was kind of looking at deducing whether or not a molecule was polar or non-polar based on the bonds and based on the geometry. If you have that information, well, then that's a perfect way to approach it. Now, when it comes to calculating electronegativity differences, I would provide you with those electronegativities so you could classify something as polar or non-polar. But generally, what I want you to do is try to visualize what that molecule looks like, and then based on the geometry, is it a polar or non-polar molecule? All right, well, thank you very much. Have a good one.